Vanakkam, Namaskar, hello. Myself Yogesh. Today I am gonna present my topic on torsion. Torsion is nothing but a twisting movement in a rod or a shaft. At first, shaft. What are shafts? Shafts are the machine element which are used to transmit power in machines. These shafts may be of hollow, solid, or tapered. Torsion. Torsion is nothing but a tension or turning force on the cross section of the circular rods or a shaft. And this and torsion can be experienced when a force on a rod is applied to twist or turn. Twisting of structural member when it is loaded by couples that produce rotation by its longitudinal axis. By this rotation, we get a torque. When uh, when a bar or a shaft is fixed at one end and another end is free, if we applied force on the free end with the diameter of the shaft as d, we will get a torque. And in this, T1 and T2 are the torques, or you can call it as twisting couples or twisting moment. And these and the unit of torque is Newton meter. And these torsion can be seen in cars, lathe machine, motor pumps. Effect of torsions. Torsion create distortion. When a shaft is fixed at one end and free at another end, if we twist from the free end, it get twist. At while twisting, it gets stressed on the shaft, which leads to eventually rupture. That causes loss of energy, as if we are studying as a torsion to prevent distortion in the shaft and energy loss, thereby improving the efficiency of the mechanical system. Okay, now torsion deformation of a circular bar. Consider a bar or shaft of circular cross section twisted by couple T. Assume that left hand end is fixed and right hand end is will rotate with a small angle phi, called as angle of twist. Angle of twist is nothing but when a bar or a shaft undergo torque, shaft will twist and cause displacement. Here we can see the displacement from Q to Q dash. And the angle produced in which it gets rotated is called angle of twist. If every cross section has same radius, then subjected to the same torque, the angle phi will vary linearly between the ends. It is assumed that plane section remains plane, radii remains straight, and the cross section remains plane and circular. If phi is small, neither the length L nor its radius will change. Okay. Then for this part, consider an element of bar dx, a small element in this shaft or in a rod. On its outer surface, we choose an element A B, C, D. During twisting the element rotate a small angle d phi is in a state of pure shear. This is a pure shear and deformed into A, B dash, C dash, D. From these, a small displacement occur from B to B dash, or you can call it as C to C dash. While displacing shear strain produced, that shear strain is represented as gamma max, and gamma max is B dash divided by AB, that is equal to R, which is a radius of that shaft or bar, into d phi, the angle with respect to dx. D phi by dx represent the rate of change of the angle of twist phi. Okay, then theta. Here we are taking d phi by dx as theta as an angle of twist per unit length or the rate of twist. Then gamma max will be r theta. In general, phi and theta are the function of x in the case of pure torsion. Theta is constant along the length, so every cross section is subjected to the same term when it is subjected to the same term. So theta is equal to phi by L. Then we can write it as gamma max is equal to r phi by L. Okay, and the shear strain inside the bar can be obtained as gamma equal to rho theta. That gives rho by r into gamma max. For a circular tube, it can be obtained as gamma minimum equal to R1 by R2 into gamma max. We will get shear strain. Okay. Then circular bars of linearly elastic material. Shear stress in the bar of a linear elastic material. It is a linear elastic material. Then we will get shear stress equal to shear modulus of elasticity into gamma, that is shear strain, right? So with the geometry relation of the shear strain is obtained as shear stress maximum equal to G R theta. So tau equal to G rho theta equal to rho by R into tau max. This relation comes from this, right? Then tau and gamma in a circular bar vary linearly with the radial distance rho from the center. The maximum value of tau max and the gamma max occur at the outer surface. So the shear stress acting on the plane of the cross section are accompanied by shear stress of the magnitude acting longitudinally plane of the bar. If the material is weaker in shear on longitudinal plane than on cross sectional plane, as in case of a circular bar made up of wood, the first crack due to twisting will appear on the surface of the longitudinal direction with an angle 45 degree to the axis of the shaft. Will subject it to the tensile or compressive stress. Then torsion formula. Consider a bar required to pure torsion. The shear force acting on an element dA, this is a small element we are taking as dA, is tau dA. The movement of these force about the axis tau rho dA. That will be tau rho dA. That is moment is equal to tau rho dA. Then the equation of moment equilibrium that shows T torsion equal to integration of A, that is moment, tau rho dA. Then we can write it as dm is equal to tau rho dA. So we can change this tau to g theta rho, that is shown it as g theta rho square dA. Then if we will integrate this part, we will get g theta ip, where is ip is the polar moment of inertia equal to, where ip is equal to pi r square r to the power 4 by 2 or pi d to the power 4 by 32 for cross section. The above relation can be written as theta is equal to T GIP, where GIP is the torsional rigidity. The angle of twist can be expressed as phi equal to theta L. That shows T GIP, that is theta into L, where this phi is measured in radians. For torsional flexibility, F is equal to L by GIP and torsional stiffness K equal to GIP by L. So the shear stress is tau is equal to GP theta, and we know the value of theta, so put it in this and we will get T rho IP. The maximum shear stress tau max at rho equal to R is shear stress maximum equal to TR by IP equal to 16 T by pi d cube. So for a circular tube, IP is equal to pi R square R2 power 4 minus R1 power 4 by 2, that is equal to pi d2 power 4 minus d1 power 4 by 32. If a hollow tube is very thin, then IP is equal to pi R2 square plus R1 square into R2 plus R1 into R2 minus R1 by 2. Then at last you will get 2 pi R cube T. Then phi d cube T by 4. At last the shear stress is tau is equal to T rho IP. In this, the limitations are the bar have cross sectional either, that is solid, or for hollow, the material is linearly elastic. And the main note is that the above equation cannot be used for bars of non-circular shape because their cross section do not remain plane and their maximum stress are not located at the farthest distance from the midpoint. Thank you for watching this video.